So I'm going to give you a lecture on astrochemistry of the interstellar medium. So what am I going to talk about? I will make a general introduction on the interstellar medium, what it is made of and how do we observe it. Then I will give some basic notions on the chemistry of the interstellar medium. And then I will introduce some general ideas about the composition of the star and the planet formation regions and the protoplanetary disk. So I will describe what they are composed of, what they are made of, and how does this composition evolves during this transition between star and planet formation to protoplanetary disks. So what is astrochemistry? Astrochemistry is a field of research that brings together astrophysics and chemistry to study the molecular composition in the universe, and the chemical processes that are involved in this composition. So the first way to study the composition of the universe is to observe interstellar medium regions with telescopes, ground-based or space telescopes. You obtain molecular spectra of these regions, and with radiative transfer models, we can determine what are these molecules, so what it is made of, and what are these abundances of these molecules in the medium. So in parallel, you can also study astrochemistry in the lab through study of the individual chemical processes, either experimentally or theoretically, that will give you microphysical data on the chemical processes themselves that you introduce in numerical models to simulate this very peculiar chemistry that you have in the interstellar medium to make either predictions to prepare new observations, to compare with the observations to try to understand what you have observed. And you can also use these predictions in hydrodynamical models of star formation to make prediction on how the star forms. Okay, so what is the interstellar medium? It's all the material that is comprised between stars. So it concerns a large diversity of regions, diffuse medium, dark clouds, protoplanetary, protostellar envelopes, protoplanetary disks, and it comprises a large diversity of physical conditions. You have densities between 1 particle per centimeter cube to 10 to 14, and temperatures between 5 and approximately 1000 K. So just for comparison, on Earth, we have small variations around 300 K, so it's comprised in between this range, but you have much larger densities on Earth, about 10 to 21 particles per centimeter cube. So I'm going to introduce here a first important notion for interstellar medium in general. It's what I call density, is the number of particles per centimeter cube. It's how we define, would say, the pressure of the medium. So the densities of the medium are within this unit. So the interstellar medium is, of course, involved in a cycle of atom enrichment. So stars will form within large, dense molecular clouds. So here you have very large diffuse medium clouds. That inside these clouds you found smaller scale dark clouds. Here you don't see very well here, but it's a black contour here is a large cloud of dust that absorb the light that is coming behind it from the stars. Inside those dark clouds you have protostars, so star in the formation. And these protostars will evolve in planetary systems. And within this is within these stars at the end of their lifetime, for the big stars, that you will form heavy atoms. So 75% of the mass of the universe is composed of helium and hydrogen mostly. That was formed during the primordial nucleosynthesis, during the Big Bang. And then within this cycle, you will form the heavier elements. And so the galaxies will be more and more rich in heavy atoms. during when you form the next generation of stars. So each generation of star will form heavier atoms, and you will have higher metallicities in the later stage galaxies. So what are these atoms? So I said helium. This is a relative abundance of the elements that is measured in the solar system, so mostly in the sun and also in the other bodies. So you have mostly hydrogen and helium, and then you have, as a function of abundance, the other elements, so carbon, nitrogen, oxygen, which are the most important ones for organic matter. And so the interstellar medium is composed mostly, these elements will be in the form of the gas, okay, atoms in the gas phase, which corresponds to 99% of the total mass. Then you have tiny, mostly hydrogen, helium, and tiny percent of other elements. And then we have 1% of the mass of the interstellar medium that is in the form of dust, so tiny little dust particles, typically with a grain size of 0.1 micron. And well, we don't know exactly how they are because we don't have, they are very far away regions, so we don't have interstellar material, but this is interplanetary dust particle, and we assume that it is something like that with fractal shapes and everything. And so here you have a picture of a dark cloud here in a different wavelength, in fact, and here it's obscure at the visible light because it's absorbed by the dust, and then when you go into infrared, the light can go through because of the size of the dust. So here you can see mostly the stars that are behind. Okay, and this dust, although they represent a very small percentage of the mass, they are very important for the chemistry, as I will show you after. Okay, so how do we observe the interstellar medium? How do we know that it is composed of molecules and dust? So I already showed you. The first thing to do is to observe the interstellar medium with millimeter radio telescopes to derive line spectra of these molecules, which are of this type here. So this is a temperature antenna. This is a unit that counts the photons that are coming from these sources. Okay, it's a radio millimeter unit that counts, in fact, the photons. Here you have the frequency at which you have observed, and so it represents the frequency at which the molecules will emit a photon, and we count the number of photons that come through. And so you have different types of observations depending on the energy of the photons that are emitted. The electronic levels of the atoms will be observable in the UV and visible wavelengths. In the infrared, emission corresponds to vibrational energy levels, and the far infrared and radio wavelengths correspond to the rotational energy levels. So just to show you, you have here a molecule, and this is vibration. This represents the different vibrational possibilities of a molecule, of a 3-atomic molecule, and the rotation is like that. And the energy of your energy level is going down here. So you need to have higher temperatures medium to observe the UV and visibles, and cold medium will be observed with the radio and far infrared wavelengths. Well, something very important in the interstellar medium is that when you observe a region, all the molecules are mixed. So the emission of all the molecules will be superimposed, okay? And so one important thing is the spectroscopic confusion. If you take a molecule like CO, so 2 atoms, it's a simple one. This is a theoretical spectra of its emission. This is the antenna temperature, so it's a unit, as I told you, in the millimeters that represents the number of photons. as a function of frequency. So this is rotational levels and emission. You have a few peaks of emission over a large range of frequency. Okay? So when you observe with a telescope, it will be easy to distinguish these emissions. And now if you take a larger molecule such as methanol, in fact you have a zoom here, which represents a zoom of frequency here. And you can see that you have much more lines within this small range of frequency where you have only 2 lines of CO. You have plenty of lines of methanol. And if you observe something like lysine, you have a forest of lines. So in the interstellar medium, all these molecules will be at the same place. So they will emit on the same regions. And you can have blending of the lines on top of each other. And so the identification of the molecules is quite complicated for some cases. Okay. So this is an actual observation of a high mass star forming region. You have the full range of frequency here, still the antenna temperature. And we will zoom in each time in frequency, and I will show you that you have a lot of lines. So you have all the peaks here, and something like that you could say it's noise. And so you will zoom in. I don't know if you see very well. Here, so this is the full spectra. We have zoomed here. So we see still a lot of lines. We will zoom here. You still appear some lines, and we keep going like that. And until a very low, in fact, and as long as you zoom, you will see lines. These are all lines. And you can even go to individual lines, and among these individual lines, you have some shapes, spectral shapes, that trace different velocity components, different physical structures in your source. So by doing this kind of analysis, we can go back to the structure and the physical condition of the sources that we observe. But you can imagine that it's a very complicated problem, in fact, and sometimes you have degeneracy of the solutions and everything, but this is how we try to understand what we observe. Another important point is the spatial resolution. We observe usually small scale objects with antennas that don't have a very high spatial resolution. So we somehow have a mean emission for something that have a substructure. I will show you the improvement of the observational capabilities. So this is a high mass star forming region, and this is the emission of the dust, I guess. So it's Sagittarius B2, and you have emission of the dust in this region. This is the size of a typical size of the region, so it's already a large scale one. And it's observed with SMA, which is an interferometer located on top of the Mauna Kea, I think in Hawaii. And this is the spatial resolution. So I don't expect you to understand exactly what 0.4 arcsecond represents, but it's already a very nice one. And then this is the emission with ALMA, which is the best interferometer currently in the millimeter range on top of the Chile plateau. This is the same resolution, but a much better sensitivity. So we have more signals, so we can still distinguish better the shape because of the sensitivity. And then this is still ALMA, but with a 10 times more spatial resolution. This is the same region with the same scale, and you can see that we have some kind of potato, and now here we have some kind of filament. So this is now what we achieve with the ALMA observations, and it's changing all our view on star formation right now. Going back in the past, I would like to talk about what are the molecules present in the interstellar medium and what we know now. So the first detections were done on simple molecules through electronic transitions. So if you remember, electronic transitions means high temperatures, so extreme medium. So it was, we first discovered was CH in 37 and CN in 1940. And then in 1963, we started observing in the medium wavelength, in the radio millimeter wavelength, and OH was observed first, and then it opened the full area of molecular discoveries of the interstellar medium. And we now have film detection on 204 species in these regions. And you have here the number of molecules detected per year. And of course, it's quite spread because we don't have a lot of numbers. So statistics, we have some years where nothing was discovered, but it's quite constant, in fact, after that. But we discover more and more complex species. They are less abundant, so more difficult to observe, but thanks to the new facilities, the high spatial resolution and spectral resolution, we have more and more complex species that have been discovered. This is a representation of the sum of all the atoms for the detected species as a function of time. And you can see that it increases with time. But here it's a bit cheating because we have discovered C60, C70, and C60 plus. So these are very, very large species. And so this explains the peaks here. But even without these species, you can see that we have an increase of the complexity that we discover. So this is an exhaustive list of the detected molecules in the interstellar medium, organized by the number of atoms. Of course, the more atoms you go, the less species you have, because it's more difficult to observe. But still, you can see that some of them, I don't know if you see very well. For instance, here you have cyclic C9H5CN discovered last year. And so there are more species on the bottom here. So we discover large species, but we also discover some simple ones recently. And this is because we had some space telescopes that opened some windows that are not accessible on Earth, that you can see in space. For instance, NS Plus that was observed, I think, with Herschel. Okay, so the dust. How did we understood that there was dust in the interstellar medium? So the first person to suggest that there was dust was Trump, this guy, in the 1930s. So this person wanted to measure the distance of the stars. So for that, he used open clusters. And there are two methods to do this kind of thing in the past. There was either the apparent diameter of these clusters or their apparent luminosity, assuming that they had the same size and intrinsic luminosity. Okay? And so plotting these two estimated distances, he could see that for the farthest clusters, the two laws, in fact, the two methods gave different results, meaning that for the farthest clusters, we had less luminosity than we would expect. And this was because he suggested that it was because there was dust in the line of sight that would absorb this luminosity, this would absorb the photons, and so you would have less important luminosity for the farthest clusters. And this was then the first suggestion of dust. And since then, of course, we have had plenty of observations, and we know a bit more what it is made of. So there are two methods to observe the dust. The first one is through absorption. So you have here a background star that emits its own photons. You have the observer, and you have a cloud in between. And what you observe is the absorption feature of the photons by the cloud constituents. And this gives this kind of spectra here. The continuum of the star is, in fact, something like that. And you have absorption features due to the dust and the constituents of the dust. So you have large ones that are characterized that characterize silicates, and you have narrow ones that are more molecules on top of these silicates. I will come back to that. Another way to observe dust is through their far infrared emission. For dust that is not too cold, you can see this kind of spectra here, but you have much less information in this kind of data. So what is it made of? It's made of mostly, so there is a refractory part, really, that is formed inside the supernovae, or shocks, very, very strong shocks. And it's made of amorphous silicates and amorphous carbons. Currently, there is still debate on if these populations are related one each other or not. We know that there are grains like that and grains like that, but we don't really know if they are mixed, if they are on top of each other, or things like that. And in between molecules and these grains, we have very likely a big population of polycyclic aromatic hydrocarbons. So PAHs, which are molecules of these types, so they can be more or less big, and they are very important because they represent a fraction of the carbon, but I will come back to that. We don't really know exactly their composition. And then on top of these grains, so the refractory grains, in the very cold regions, we have a layer of molecules that will come accrete on those grains because of the very small temperature. And these species are mostly water, CO2, CH4, OCS, methanol, and NH3. Something that is still one of the big questions about the interstellar chemical composition is the diffuse interstellar bands. So since 1922, so it's a long time, we have been observing some absorption feature in the UV, visible, and infrared wavelength in many directions of the galaxy, and also in other galaxies. Okay, wherever you look, you will see this absorption feature. And the strength of this absorption feature is not strongly correlated with each other. So each of these, we think that each of these absorption features are carried by a different molecule. Okay? It's made by a different species. And there is many substructure in these absorption spectra. So we think that they must be caused by large molecules. But until up to now, we have not been able to identify any carrier except for C60+, which was attributed very recently to some of the future, but cannot explain everything. So we think that there is probably a large population of carbon-bearing molecules of composition we don't know, that is present there, that evolves with the conditions, but we still haven't understand what it is exactly. Okay, so I already told you a little bit, but these molecules that we observe, we use them to probe the physical conditions and the kinematics of the regions. These are the tools that we use to understand what we observe. Okay? So for instance, I show you here a way to probe the kinematic. You have a spectra in red of a molecule observed in a protostar, so a star under making, which has a very strong, a very complicated structure with a center, with an outflow, with a disk around, and etc. And in fact, the spectra will show different shapes depending on what is present inside this object. So we observe this object, of course, with a large beam telescope. So we have no spatial resolution, but these spectra can help us understand. Here you have a small narrow peak that in fact corresponds to the envelope itself. And we have another wing here that we know is at higher velocity, and that represents the outflow, because the outflow has a velocity that is different from the rest of the structure. And then we also use the emission of the molecules to probe the temperature and the density of the regions. So the difficulty in this to do that is that it is usually not a local thermodynamic equilibrium. So if you are not at local thermodynamic equilibrium, you cannot estimate a single temperature. The temperature is determined by the collisions, and so you determine excitation temperature by molecule that will explain the energy population of each of the molecules. But by doing that and using several probes, we can get estimates of the physical conditions. Okay, so I will switch to the chemistry. So first, some basic notions that I need to introduce about chemical reactions. So you have here two different chemical reactions. Well, no, sorry, you have one chemical reaction, but producing two different channels. So species A plus species B will produce C plus D or H plus H. And I will call K1 and K2 are what I call the partial rate coefficients. The total is the sum of the two and represents the velocity at which the reactants will disappear. And the unit is centimeter minus 3, second minus 1. And then I will call branching ratio of the reaction 1, the fraction of the total rate coefficient, K1 over K total. Okay, you understand what I mean. And then branching ratio 1 plus branching ratio 2 equal 1. So in the interstellar medium, we have a particular chemistry because we are always at non-equilibrium and not steady state chemistry. So I want to make the distinction here because you're probably maybe more used to equilibrium chemistry, which occurs at high density, where in fact you minimize the free energy of the system. All chemical reactions are balanced, and it's a closed system. Okay, so you compute a solution at equilibrium. In the interstellar medium, the system is never closed. We always have energy brought by the system in terms of photons, cosmic ray, and everything. And in most of the cases, we are not in steady state, meaning that the system does not reach, well, a steady state. So if you take two reactions, A plus B gives C plus D, or C plus E gives F plus G, you can write that the variation of the density of the species C as a function of time is this equation here, and N represents the densities of, or the concentrations of each of the reactants. So for the species D, you form it through this reaction here, and you destroy it through this reaction. And so you can compute such systems for all the species that are present in the interstellar medium and all the reactions that couple your species, and you have this kind of equation for each of the species. And so we are not at steady state, meaning that these equations are not at zero. So you cannot find a single solution, but you have a time-dependent solution. What are the chemical processes that you find that govern the chemistry in these regions? So you have a schematic view here of the different medium of the interstellar medium. So you have diffuse clouds that are characterized by low densities and large photodissociations. So you have a lot of photodissociations either by the UV photons, I will come back to that after, or cosmic rays. And you have mostly atoms because molecules are destroyed by the photons and the cosmic rays. And then you have large clouds where you have dust that shields, that absorb the photons outside of the clouds. And so inside these clouds, you have a little amount of photons. You have little, well, cosmic rays will still go through, but you can have a lot of chemistry going on, and you can have formation of your molecules. And it is inside these clouds that you will have a star that will form. So first protostars and then protoplanetary disks that are made of this material. And you have a lot of chemistry going on here. So what type of chemistry? You have gas phase chemistry. So these are the main type of reactions that occurs in these mediums. So ion molecule reactions, photodissociations by UV photons or cosmic rays, electronic recombinations, neutral-neutral reactions, so reactions between two neutral species, radiative associations. These are this kind of reactions where you have just association of two species and two that will emit, the recombination will emit a photon to stabilize, and electron attachment that will form anions. So the source of ionizations, there are two sources of ionization. Ion neutral reactions are very important in the interstellar medium. And there are two sources of ionization. The first one are the UV photons that are surrounding everywhere in the galaxy or in other galaxies, and that are emitted by massive stars. There are massive stars everywhere that will emit UV photons. And so all the material is bathing inside a soup of UV photons that will produce photodissociations. And then there is a second source of ionization, very important, coming from the cosmic rays. So through the galaxy and other galaxies, there is also a flux of high energy particles that travels everywhere. Okay? They are also coming on Earth, but they are so rare that usually they don't interact a lot with the material. But for the interstellar medium, it's enough. So this very high energetic particle, by the way, we don't really exactly know their origin. We know they are there. We can measure them. They are probably coming from black hole or AGN or very, very violent environments in the galaxy or other galaxies, but we don't really know where. So these very high energetic particles that are composed of protons, electrons, iron nucleus will travel through everything. And in these clouds, this is the representation of the cloud, it will penetrate and interact with the material. Although it's a rare process, it's very important because it's very energetic. So H2 and helium are the most abundant species, so it will first interact with them, producing, so first ionizing H2, and then producing high energetic electrons that will again interact with the material and that will produce photons. So inside those clouds, the external UV photons do not penetrate because there is dust that will absorb the photons, but inside the clouds there is a production, in situ production of photons through the cosmic ray particles by an indirect process. And this is very important for the chemistry. Another major process is the interaction with the interstellar dust. So there are these tiny particles of dust in the clouds, and the molecules in the gas phase will collide with this dust with a frequency that depends on the density of the dust, the density of the medium, the temperature, etc. And when they collide, they have a probability to stick. In fact, they will create a low energetic van der Waals liaison with the dust, and they can stay on the dust. On the dust, they can diffuse, they can move, depending on the dust temperature. And if they move and they encounter another species, they can react and produce a new species. This is how we believe that complex organic molecules will form. And so, in these regions, with time, you will build up on top of those grains a mantle of icy molecules. Icy, we usually say icy because it's mostly made of water and traces of other molecules such as methanol, formaldehyde, NH3, CO2, CO, etc. And then in regions where the temperature is high enough, this material will go back in the gas phase. The van der Waals liaison will be broken by the temperature, and they will evaporate. Okay, so I show you a small animation on how we believe water form on top of this grain. So this is a star-forming region with a scale, and you zoom in onto one grain. We assume that they are of this type. And on these grains, you have these atoms. So oxygen is in red, and hydrogen is in white. And so the hydrogen is much more mobile than the oxygen because it's lighter. Okay, so it will move around much easier. And you will form, in fact, here you form O2, H2O, and you probably had also an H2 somewhere. But H2 is not bound to the surface, so H2 will go back in the gas phase. And little by little, you form these ices like that. Okay, up. So how do we, I have only 2 slices on that. How do we construct this? Because one of my goals, for instance, in my field of research is to construct numerical models to simulate this chemistry. And how do we do that? So the individual processes are studied in the lab, either by theoretical calculations or experimental measurements. And I show you here an experiment. This is an experiment that is set up in the observatory in the University of Bordeaux, which is called CRESU. So it's in French, sorry, it was invented by French and they kept it. So cinétique de réaction et écoulement supersonique uniforme. That is used to study gas phase chemical reactions, neutral gas phase chemical reactions of these types. Okay, I'm not going to describe, but basically we try to reproduce the condition that we observe in interstellar medium and measure the individual rates of the individual reactions. And they also do that for, using theory. And you have here an example for one reaction. I believe it's O plus OH or N plus NO. I don't remember. But it's a simple one. You have the partial rate coefficient of this reaction as a function of temperature. The solid lines are different theoretical calculations. And the dots here are experimental measurements. And you can see that for the same reaction, you can have quite a different results because it's very difficult at low temperature to either measure or calculate that because there are many of processes that enter in competition and it's very difficult. So then all these individual rate coefficients are used to construct numerical models. And in fact, I told you, I did not give you any numbers, but these individual chemical processes are counted by thousands, okay? And so it's very difficult to, gather all this information and have a good quality on this data for thousands of chemical reactions. So this is an example. So all these processes are stored in this format. So it's line by line, it's a chemical reaction. So you have reactants here, products, and these are parameters used to determine the temperature-dependent rate coefficients. And these are stored in databases, public databases. You can have a look if you want, where we try to store all the chemical reactions useful for the interstellar medium and the information that we can gather on them. And then we construct subset of chemical reactions for the numerical models that contain more than 10,000 reactions for about 600 species. This is the kind of system that we study. The most important species that we have, which is H2. H by far is the most abundant element in the universe. And so H2 by far is the most abundant molecule in the universe. And it was not, it took some time to understand how it was formed in the interstellar medium. So there are several possibilities. The first one is a radiative association of this type, but to be stabilized, the HH species to be stabilized, complex, voilà, sorry, the HH complex, to stabilize it, you need to emit a photon in an impossible transition. So this reaction does not occur, in fact. And other processes are through ionization states, so either H- or H2, but the ionization stage of the interstellar medium is not high enough. You cannot account for the H2 formation through these reactions. And so it was proposed that H2 was formed on the grains. And in fact, it's the only way to form H2 is to use the surface of the grains to stabilize your complex. So what you have is first you have a sticking of the species on the surface, sticking of H, moving of H, encountering another H, forming H2, stabilized by emitting the photon that will be absorbed by the dust below it, and H2 that is not really bound to the surface to go back into the gas phase. And there are plenty of experimental and theoretical studies to try to understand exactly the microphysics of this process, and at which, because we know H2 is everywhere, we observe it in conditions where we would not think that H2 could stick, that H could stick on the grains, but we do observe it. So there are plenty of processes that are very difficult to understand to reproduce this H2 in the interstellar medium. And it also brings the question of the formation of H2 in the first generation of galaxies where the dust was not present, because we said we needed several generations of stars to form the heavy elements that will form your dust. So how did H2 form in these very early galaxies is still a matter of study in that field. So O2 and H2O, these are the way they form through a gas phase. So through gas phase ion molecular reactions. So everything starts, most of the chemistry will start with the cosmic ray ionization of H2. So this reaction is of particular importance, and this is a gas phase formation of water, but we have seen that you also form it very efficiently on the grain surfaces. Okay, I'm going to give you an example for O2, because it's still a very one of the mysteries of the interstellar medium. So the gas phase chemical models that I briefly described before will predict that you form a lot of the O2 in the gas phase. So this is abundance as a function of time. So you could say also concentration or anything you can, it's just a way of counting the molecules as a function of time for a dark cloud. And so you form CO, you start from atoms, you form CO, and you form a lot of O2. And so these models predict that the ratio O2 over CO is 0.5. So there was a big hunt for O2 in the interstellar medium. CO is observed very easily everywhere. It's also a very abundant molecule, but O2 is not. So there was a big hunt. starting from ground-based telescopes. So O2 is not easy to observe because we have O2 in our atmosphere, and it will absorb some of the frequencies cannot be observed from the ground because of the O2 in the atmosphere. So they started to look for isotopic transitions of O2 in galactic sources, or the main isotopic O2, but in extragalactic sources using the Doppler shift due to these extragalactic velocities, and they couldn't find O2. Okay, and the value, the upper limit, the ratio was smaller and smaller. And so they in one of the telescopes, the space telescope that was launched in 1998, SWAS, part of the scientific goal of the telescope was to look for O2. And they couldn't find O2. And in fact, they found an abundance for O2 that was 2 orders of magnitude smaller than what was predicted. And so they built a second space telescope. That's the main goal for the astrophysical part was really to detect O2 in the interstellar medium. And again, they couldn't find O2, and the limit was even 10 times smaller. So then, after reprocessing and reanalysis of the data, they claimed the detection of the molecule at the nearly at the upper limit detection that they claimed before. And now it's been confirmed with a new space telescope that was launched a few years ago now, Herschel. And they found O2 in 2 sources only. And they have a lot of non-detection of the molecule. So it's a rare molecule. It's not present it's not present in many sources, and the abundance in the sources where it was observed is much below what was predicted before. So why is this? So there are plenty of theoretical studies to try to understand that. I think that one of the most simpler explanation is in fact the dust. Here is a prediction of the pure gas phase model that I showed you. There is no dust in there. Now, if you add the dust, you can compare. The O2 is in the pure gas phase is in green, and you have O2 here in red when you had gas surface chemistry. And in fact, the oxygen is depleted on the grains and will be hydrogenated to form water, and will be used by the chemistry to form other molecules. And so you have little amount of oxygen that is available in the gas phase. And if you want to generalize that with the diversity of the physical conditions that you can find in the interstellar medium, you will see that, in fact, you predict that O2 is not very abundant. This is a statistical way of looking at the O2 abundance in the gas phase as a function of densities, considering all the different mediums that you can have in the interstellar medium. And this is the upper limit, observational limit. And you can see that there is a little amount of points above this observational limit. So we don't expect, in fact, a lot of O2 in these regions. But it took 30, 40 years to reach to this conclusion. Recently, the question of O2 in the interstellar medium was brought back to the general scientific public by the detection of O2 in the comet, 60P comet, by the Rosina team that estimated it to be a few percent of the water in the comet. There is another instrument on Rosetta that estimated a very large fraction of the O2 as compared to water, but I think that it's been rediscussed recently. So I would say that maybe we have O2 a few percent of water in the comet in our solar system. So there was a long debate in the literature to try to understand this O2, because it's difficult to imagine that you have O2 in ices that is not hydrogenated. So you would mostly have O2, H2 rather than O2 by itself. But the H2O2 observed in the comet is very low. So they really argued to say that there was O2. So I'm not going to enter into details. There are plenty of works that say that it's primordial O2, so O2 coming from the interstellar medium, stored on the grains, stay on the grain, and just be incorporated in the comet. There was a chemical result that proposed that the O2 that they observed was a dismutation of H2O2 that is evaporated from the surface, but it's not convincing neither. And then there are several publications that try to say that this observation is in fact, how can I say, experimental bias of the comet. So it's a wrong measurement, but it's not true. But okay. The question is O2 abundant in interstellar ices, and maybe we will have more answers with the GWST that will observe at very high sensitivity the interstellar ices.
The places where stars and planets are born are among the galaxy's most beautiful locales. These cosmic landscapes change as new generations of stars light up and disperse their birth cloud. But the youngest stars seen here are already perhaps 1 million years old. Hardly toddlers.
Stars and planets form in the dark, inside vast cold clouds of gas and dust, such as these pillars imaged by the Hubble Space Telescope.
The dust is so thick we can't see the infant stars inside, at least not with visible light.
With infrared light, Hubble can see through all but the thickest dust. Yet it's in those dense knots that the youngest stars are forming.
To peer inside them, astronomers need the James Webb Space Telescope.
With a mirror larger than Hubble's and performance optimized for the infrared, Webb will give astronomers their closest look yet at stellar birth.
We're flying through a computer model that represents astronomers' best ideas about the star formation process.
Reddish colors indicate thicker dust. The temperature, less than 400 degrees below 0 Fahrenheit.
Or less than 240 degrees below 0 Celsius.
That pinwheel ahead is a protostar, perhaps 10,000 years old. Protostars arise when a dense knot of dust, less than a light year across, collapses. But the details of the process are not well known.
Elsewhere in the cloud, another protostar is preparing to build planets. As the cloud that created the protostar collapsed, it flattened into a disk. The disk we see here is 600 times the size of Earth's orbit around the Sun.
If placed in our solar system, it would extend far beyond the planets.
In this computer model, the disk continues to accumulate gas and dust from its surroundings for thousands of years. Eventually, the disk fragments, producing dense, bright structures. These may become sites where giant planets form.
Later, during another phase of construction, smaller Earth-sized planets may take shape.
At least, that's what scientists think happens. It will take the Webb telescope's keen infrared eye to see what's really going on in the cold heart of stellar nurseries.
What I wanted to show you here is to make you understand that the planetary systems are really formed from material that come from the interstellar medium and undergo a very some modifications, but the material will be the same. So the chemical composition of what will form your planets will depend on what has happened before, in fact. Okay, so the chemical composition starts in the diffuse medium, and you have here a representation of the sequence of this sequence of evolution that starts from the diffuse medium that will form large cold cores in which, so here you have mostly atoms. The densities are quite small. I don't know if you see. The temperatures are high in my standards, not in yours, but in my standards they can be high. And then it will form dark clouds. In those clouds, you will be shielded from the UV photons. So you will form molecules. The chemistry really starts there. You have a temperature that is really cold. You have the formation of simple molecules. They can be large, but they will be non-saturated molecules, and some of them will be just hydrogen, carbon, nitrogen, no oxygen. There is not much big oxygen molecules. Then in those clouds, you will have the formation of the protostars from this material, and so the chemical composition will keep evolving. Okay? And all these processes are time dependent, so there is no steady state. You always depend on what has happened before. The densities will be higher, but most importantly, the temperatures will be higher. And in particular, the temperatures will be around, for some amount of time, around a few tens K. And at these temperatures, you will move species on the grains, but you will not desorb them. Meaning that on the grains, you will be able to form the big, large molecules. This is where you expect the large molecules to form. And from inside those protostars, some of the material will end up in the stars, but some of the material will stay out and become the protoplanetary disk in which you will form your planets from this material. Okay? And so the protoplanetary disks are very small objects, and currently it's the field of research that is exploding with ALMA, because we are discovering what they are. We start to discover how they are, what are their physical conditions, what are their chemical composition, but we still don't really know, I will show you after, what they are made of. And then, of course, your protoplanetary disk, there is another transition towards comets or planets and everything, in which there are plenty of unknowns about the chemical composition. Is there a link? Is there a reset? Is there an inheritance? I don't know. Okay, so about star formation, maybe the most important result in the last 20 years was to understand the structures that are forming in the interstellar medium in which the stars are formed. In fact, we discovered with Herschel, which was a satellite launch a few years ago, that the interstellar medium is organized in terms of filaments. Okay. So the stars are not formed in spherical objects or everything. They are formed inside these filaments in denser region of the filaments. And this is an observation at several wavelengths that you can see, and you see, in fact, you can see here it's the modeling. You can see here in the infrared observations the filamentary structure, and in fact, we are now able to reproduce these filamentary structures with hydrodynamical models. This is a hydrodynamical simulation that starts of a turbulent cloud that starts from a spheric one, but with turbulence inside, and the material organizes itself in filaments. So we have zoomed in, and this represents denser regions. You can say it's the density. And you start to see the formation of the stars inside these filaments, and they are then ejected in the interstellar medium. And so the question is there a link between what is observed in the interstellar medium, the large complex organic molecules, and what we see in comets? Comets are supposed to be the most primitive objects of the interstellar medium of the solar system that would have inherited its composition, at least partly, from the interstellar medium. So there are plenty of people that try to link one each other. So is there a link? Is there a reset of the chemistry in the protoplanetary disk? So related to that, what is the chemistry of the protoplanetary disk? And do we really need this link? Is there a reformation of the molecules in the protoplanetary disk or not? So some people have tried to compare the chemical composition of the comets and the interstellar medium. So this is a now only nearly 20 years ago comparison. This is the abundance of species over abundance of methanol in the interstellar medium as compared to what was observed in Hale-Bopp. And well, if you see that, you would say, yeah, straight, good correlation. It's really nice, but these are only two star-forming regions. These are, in fact, four star-forming regions with very different histories and physical conditions, and you don't see any error bars on that. So the question is, how can we compare? So first, we can make a comparison between what is observed in comets and what we predict in star-forming regions. And this is, in fact, a comparison of this type. This is a model of formation. Well, sorry. This was obtained with a chemical model of a star-forming region, distinguishing the disk. Well, maybe it's a bit complicated now. Well, what I can say is that if you make such comparison between predicted abundances and comets, you find some similarities. Okay, there are some molecules. The comets are in gray and green, and the other colors represent what you can find in the protostellar regions. And so in yellow here, I have shown what are the molecules that are in fact similar in the comets and what we have predicted by our model. But this comparison was made before the Rosetta area. So before we had much better chemical composition of the comets. And in fact, when we did that, we found that the comparison was quite difficult, because if you look at the comets that have been observed, you find a large diversity of chemical composition, in fact. There is a variation of the abundance within the comets. So now what you can do is to compare what is observed in comets and what is observed in protostars, so the formation region of star being formed. And I haven't put any numbers because, again, there is a large diversity of chemical composition, in fact, both in comets and both in star-forming regions. But what I show you here are the molecules that have been observed in Rosetta, in the comet by the different Rosetta instruments. And in fact, except for this one, all these molecules have been observed in star-forming regions. And again, I don't put numbers because I don't believe that we can really make a detailed comparison. So there was also the detection of glycine in this comet, and glycine has not been detected in the interstellar medium. There are some claims, but all the lines of glycine are not observed. So for now, we have not detected glycine in the interstellar medium. And so what about protoplanetary disks? So the next step of the stellar evolution, well, of the interstellar evolution, you have here a schematic view of a protoplanetary disk. So here the star has formed already. The cocoon of material around the star was disrupted. And so you have only a flattened structure around your star that is rotating around it, and in which you will form the planet. These are small objects as compared to what we have shown up to now. This is there is a few hundred AU, and these are very small objects as compared to the other one, and they are not very close to us, so it's very difficult to observe, in fact. And these are the different instruments that you can use at different wavelengths to observe. So depending on the wavelength, you will observe at higher spatial resolution, so you will get closer to the star. And most of the molecular observations can be done with ALMA. This is really the instrument to do that right now. And you can see that you will observe outer part of the disk. So it is difficult to go inside and really have an insight of what is inside the disk. So this is an artistic view. Of course, we don't have this kind of image. But what has been observed up to now in terms of molecules in those disks are listed here. This is what we have seen in this disk. And, well, these are mostly simple molecules. These are the same as in the interstellar medium. The abundances are not so different, neither of the interstellar medium. And for the complex molecules, well, you can see that it's still not very complex. And in fact, it's very, very difficult. And the sensitivity, well, the line fluxes of these molecules is very small. And it's either a problem of abundance or excitation of the lines, because the disk I will show you are not very hot. And these are actual ALMA images of what we have of protoplanetary disk. This is really the revolution for us. You have, I don't know how many, but you have a few samples of protoplanetary disk. And the big revelation was to see that in almost all of them we see gaps. We see rings. Okay, this is a dust. This is a dust distribution, but we also see them in molecules. So we have rings of material and gaps in between. And we believe it's the formation of planets, massive planets, that is under construction. So there are rings, and they are nicely distributed, and in some cases there are spiral arms. Unfortunately, I don't think you can see very well. In this one, for instance, you see spiral arms. So there is a big field of research trying to understand what could cause the different geometries of the disk, and especially the fact that they don't all have rings or they don't all have spiral arms. Alors, so this is what we believe is the physical condition in this disk. Alors, it's a bit complicated. I just want you to focus on temperature here, for instance. And this is Z over H. So Z is the altitude, R, sorry, Z over R. Z is the altitude, R is the radius. So it's a ratio between Z and R, allowing to see the small radius. If I had put just the radius, the altitude as a function of radius, you would not see, you would have seen nothing here because the disks are evasing toward the outside. And so what you can see, this is the log of the temperature. The disk is hot in the upper part, of course, and becomes very cold in the midplane. So it's a half a disk, I would say, okay? This is the midplane here, and the altitude above the midplane. And so the disks are very cold in here, and there is a small region coming toward the star. The star is here, where you have a temperature above 10 K. But most of the disk midplane is very cold. This is why you don't see a lot of molecules. Everything is frozen onto the grains. And so what are the chemical processes? This is the simplest way of looking at the disk. You have a cut here of the disk. You have the star. And we believe that there are three different phases in new protoplanetary disk. You have a midplane here, which is very cold. That's there is almost no chemistry because everything is on the grains. And then you have what we call a molecular layer here, where the density is not so high, the temperature is not so low, and this is where you have most of the chemistry. You have a gas grain chemistry, but also chemistry in the gas phase. and then you have a photodissociated region above in the upper part, where you have a photodissociation of the species, and you don't have a lot of molecules. So when you try to observe a disk, you try to observe this tiny portion of the disk. So it's very small, it's very difficult to understand. So the question that I wanted here to address is, do we really need to have molecules coming from the interstellar medium to have complex molecules in protoplanetary disk? Well, in fact, you don't. This is a simulation of a protoplanetary disk chemistry, assuming that we start from nothing, from atoms. So we don't have any inheritance from the interstellar medium. And this is the CH4 abundance, this is the methanol, and CH3OCH3 abundance. This is the abundance, this is the radius, and still Z of altitude of a radius. And in fact, we form the complex organic molecules within the disk. You don't need any inheritance from the interstellar medium. We are able to form them within the disk. And I will end with this transparency here, showing that this is the first observation of very complex organic molecules within a disk, in fact. It's a very recent paper published in Nature Astronomy. I told you everything is frozen onto the grain. So how can you have access to this composition? And in fact, they have observed a very specific type of object, which is called Fuori. And these stars, they have outbursts of energy time to time that will heat up your protoplanetary disk. So in fact, here it's a quiescent phase. Here you heat up, and you will evaporate the ices and farther away from the star, so easier to detect. So because of these specific sources where you have outbursts, you will evaporate the species from the grains, and you will see them in the gas phase, and then you can measure them because it's farther away from the star. And they have found in the gas phase large abundances of these species inside those protoplanetary disks. So for us, it's a very important clue, and it shows us that, yes, we form the molecules within the disk. And in fact, you don't really need to have the... well, it reproduces what we accept from the models. So we don't need the interstellar medium to form the complex organic molecules in the disk. And I will end.